Here is a power amplifier with 16 junction FETs in parallel. It has ferrite cores on the input and on the output. And here is the schematic diagram. A voltage divider to put 3 volts on the gate to allow a bigger resistor on the source, which gives a better current feedback for very low frequencies, the 1/f noise that might modulate the signal in the transistors. 16 times J310. This transformer has 3 turns and 5 more turns to give a step up, 8 divided by 3, which is 2.66 times. And the same number of turns on the drain as on the source. The output impedance here, despite the step up, is fairly low. So to get 50 ohms, I have put 33 ohms in series here. And to make it pure resistive, I added 680 pF in series to compensate for the leak inductance in this core. 2.2 microhenries here, and there is a capacitor here, 10 microfarads tantalum to keep the noise very low on the gate, the low frequency noise. This amplifier is connected to the previous amplifier that I described in the previous video. It has now an output transformer with a 1.4 times step up of the voltage, and then the output impedance is 28 ohms. And in front of this amplifier there is the crystal filter. So the whole box here is a selective amplifier at 10 megahertz. I will first establish the noise floor. And you can see on the screen I need to put the screen on the box. And you can see it has some effect, not so much in decibels. It's only 0.15 dB or so. I have connected the box now directly to this low noise amplifier, and the noise floor I see here is 3.46 dB. I now move the cable to this noise source, and I have set it to get the same noise level as I had before with the amplifier, which was 3.46, and now I have 3.46 from the noise head, and that is when it is set for a noise figure of 7.4 dB. So the noise I have is 7.4 dB above room temperature. I am now sending plus 14 dBm into the unit. That's about the maximum level that the crystals can manage. The output power I see then is 11 dBm, and that is through this 20 dB directional coupler which goes to the box. With the noise floor 7.4 dB above room temperature, I have minus 166.6 dBm per hertz. And the power is 31.2 dBm, so noise is minus 197.8 dBc per hertz. Now, this is assuming that the amplifiers do not modulate a strong signal, and that turns out to be not very correct. Here is the noise from the noise head when it's cooled, and what you see here is the noise from the amplifier when there is no signal input to it. And it's now 2.65 dB. It was 3.46 before, but this is because of the losses through the notch filters. I have set the bandwidth now to 10 kHz, centered on 9.95. And then I start to send the signal into the amplifier while looking at the noise level. I start at 0 dBm, and as you can see, very little happened. So I step power upwards in steps of 1 dB. And now we start to see a difference, but it's small. And that is at an input of 7 dBm and with an output power of 4.3, as you can see here. So this is not bad. 24.3 dBm output, but there is still 6 decibels more I want. Here you can see spurious things from crystals, and I think that is from the notch filters, but it could also be from the amplifier. I will look at that later. We were at 2.65, and since I'm stepping up by 1 dB, I can tolerate losing about 1 dB here. Oh, here the noise starts to go up rapidly. So I go back one step and say, this is a performance I should be able to see when running this as an oscillator. The output is 9 dBm here, means 29 dB output. To get a similar noise floor from the noise head, I have to set it to 9.2 dB. So what I actually see with 12 dBm input is a noise sideband at minus 193.8 dBc per hertz. But when I increase the power, I go up 1 more dB and 1 more. You can see noise increases rapidly. And here, very much. So there is some odd phenomenon going on here. More interesting is, well, I have to change the scale to see a little bit better. Like this. The maximum level I can get. 1 more dB here, then the level actually, the noise went down a little bit. And looking at the output and step 1 dB downwards, it makes no difference. And only half a dB for this 1 dB step. So I can increase the supply voltage, and that gives me more power. And then stepping up the signal generator to 15 dBm, it gives me now 31.5. But as you can see, noise is very high. So I have to step down 1, 2, 3, 4 is not needed. 3, And I can change the supply voltage. It's now 25, and I turn it downwards. And here things go wrong. That is at 16 volts. So and I can try the supply voltage here when there is a modest increase of the noise. And as it turns out, there is a sweet point at 20 volts. If I go up to 24, I have a lot of noise here. And if I go down to, let's say, 18, I also have noise. So it is sharp minimum. This is an odd phenomenon that I did not expect. I've tried to understand what is going on here. A bigger ferrite on the output did not help. So I'm looking for other problems. These red wires, one go to the oscilloscope, the other to the spectrum analyzer. They are both connected through a 1 pF capacitor here to the emitters of the bipolar transistors, the MPS H10. And there I see something very clear, which is a problem. I have to put the lid here to get a reasonably clear screen. Now you can see the noise floor, and I have some instruments running that create interference. But when I increase the signal level, I come to a point where there is suddenly a lot of noise. And 1/2 of a dB down, and it disappears. This is what I see in the spectrum analyzer. I go down 1 dB and 1 more dB. So something is starting to happen here, high up in frequency. And on the oscilloscope, now there is no noise, and now not much, but now there is a lot of noise. So there are oscillations that start at a certain operating point of the transistors, and which one I don't know yet. To get rid of the oscillations, I have put 22 ohms and 0.1 microhenry in the feedback from the antiphase of the source to the gate. And then I had to remove this 3.3 pF capacitor. I have taken out the current here from the sources as well as from the load, and brought that back to the previous stage, which is the input for the power amplifier, and wound 2 turns on this transformer to make the impedance lower as seen from this point. I made it about 150 ohms. That's about the maximum current that this can supply. I mean, the output impedance at this point is about 50 ohms, but I cannot load by 50 ohms because then these transistors would saturate. But I can load with 150 ohms, and as a result, the output impedance that I see here is now higher. which means I can make this resistor smaller. And it's now 12 plus 15 ohms. Before doing these things, I have replaced this transformer with one that has much better coupling between the windings and also much better tolerance for DC current. That didn't help, but I could make this capacitor much bigger. It's now 0.1 microfarad. So I have now 50 ohm output impedance. And I think this is, well, one more thing. I have changed the voltage divider here. Sorry. The voltage divider here from 3.4 kilo ohms to 2 kilo ohms. That made a small improvement. And the noise that I see, it comes when the 16J310 run into saturation. And I will now look at the result that I have. Here is the noise head cold. I've calibrated to show 0. And this was the readout from here. That is the amplifier with no signal present. The difference is 2.74 dB. I am now looking at the noise head and I am sending current to it to get a noise level that is the same as I had before. Well, I have to wait. Now the noise is just a little bit higher, 2.76, so that is accurate enough. And that's for a noise figure of 9.4 dB. It's on the low range, 9.4. This means that the noise floor without any signal is 164.6 dBm per hertz. I'm now sending 13 dBm into the unit on the center frequency 10 megahertz. And as it turns out, there is some compression. The noise floor is now only 2.4 dB. So compressing in the power amplifier reduces the sideband noise at a wide range. What happens at the close range, of course, I don't know. But I will evaluate what 2.42 means. Now I'm looking at the noise head and I have 2.45, close enough to 2.42. The noise figure then is 8.6 dB. The power I see is 11 dBm, and that's through this 20 dB directional coupler. So what comes out from the box is 31 dBm. So this means 8.6 dB minus 165.4 dBm per hertz. And with the carrier at 31 dBm, the noise at 50 kilohertz is at minus 196.4 dBc per hertz. That's the total noise. Presumably half of it is AM and half of it is FM, because I don't think this is anything else than amplifier wideband noise. So the phase noise is likely to be minus 199.4 dBc per hertz. And it seems this will be good enough for starting to look at other things.